Hello everybody, my name is Anke Hagen. I'm from the Technical University of Denmark and I would like to introduce electrolysis today. I will start giving you a few of the basic principles of electrolysis. I will introduce the materials that we are using today, what we have to do to get from the materials to the systems, and then I would like to finish with giving a status about the commercialization. Let me start with some basic principles. The first equation shows the splitting of water into oxygen and hydrogen. There are more possibilities for electrolysis. For example, you can split carbon dioxide into carbon monoxide and oxygen, or you can execute a co-electrolysis where you mix water and CO2 and you obtain a mixture of carbon monoxide and hydrogen that is actually very well known as synthesis gas. In the presentation today, I will focus on the water electrolysis. One of the first questions you would like to ask is, what is the efficiency of the process? The efficiency is defined as what I get out versus what I put in. What I get out from an electrolysis process is hydrogen, and what I put in is electrical energy. And that can be translated to thermodynamic terms. More specifically, we can translate hydrogen into a reaction enthalpy, that is the energy content, and the electricity we can translate into the Gibbs free energy. And here now we have the equation to calculate efficiencies. In the case of water, there are two opportunities. One, water can be in the liquid form when we start, or water can be in the gaseous form. And that determines which thermodynamic values you are using for the calculation. For the case with the liquid water, you would use higher heating values, and in the case of gaseous water, you would use the lower heating values. What you then obtain is an efficiency of 121% theoretical efficiency for the liquid water case and 106% for the gaseous water. That seems counterintuitive, that an efficiency can exceed 100%, but that is due to the definition that you are using the reaction enthalpy and the Gibbs free energy in the calculation of the efficiency, and you disregard any heat that is involved. That also means that the reaction enthalpy is always larger than Gibbs to get to the larger than 100% efficiency. And how that is possible becomes clear when you look at this basic correlation between Gibbs and the reaction enthalpy, where the third term comes into play, the change of the entropy. Particularly reaction enthalpy, you know that when there is a minus, means it's an exothermal reaction, or it's positive, the change, when it's an endothermal reaction, as it is the case for electrolysis. The entropy term expresses how reversible or irreversible the process is, or how the state of disorder is. And as we are going towards a state of a higher disorder when we do electrolysis of water, then this is a positive term. That means H is always bigger than the Gibbs energy, and we obtain a theoretic efficiency exceeding 100%. Now we are talking a lot about electrical energy. How can that come into play with this equation that is shown here? The electrical energy, here expressed as a voltage, correlates with the Gibbs free energy by the number of exchanged electrons and the Faraday constant. There is another very important principle connected to electrolysis, and that is the thermoneutral voltage. Electrolysis is an endothermal process. However, in a system, you also generate heat, among others, because of internal resistances, and that is creating heat. And the thermoneutral voltage is precisely the point where the formed heat is equal to the heat needed for the electrolysis reaction. And that can be calculated through this equation. And you see there are two values we obtain. For the first case, 1.47 volt is for the liquid water splitting, and the other value, 1.29 volt, for the gaseous water. So these are the basic thermodynamic terms we need to know for electrolysis. When we have them in place, we can also see how do they develop as a function of temperature. You see that there is a break here at 100 degrees centigrade when water turns from liquid, left side, to gaseous on the right-hand side. And then let us follow how the energy contributions change with increasing temperature. The total energy demand, as expressed as the reaction enthalpy, is fairly independent on the temperature. However, the electricity needed for electrolysis, this input goes down when we increase the temperature. That means at higher temperature, I can supply more of the needed energy in form of heat, or entropy times temperature. Heat is typically a cheaper and more easily available form of energy compared to electricity. So this figure shows it is actually attractive to carry out the electrolysis at elevated temperatures. With these basics in place, I would like to come to materials that are used in the electrolysis process. And before doing that, I just come back to the basics. What is the electrolysis? This is an experiment you can actually do at home. You start with a beaker, fill it with a water solution, and then you put wires into it and connect a battery. When you do so, gases start to appear, oxygen on one wire and hydrogen on the other. The terms to describe this are electrolyte, this is the aqueous solution, and the two wires are the electrodes. This is, of course, not a very suitable concept for a large-scale electrolyzer plant. What is being done is you're changing the geometries. You make the electrodes into sheets or plates that sandwich the electrolyte in between. One of the main functions of the electrolyte is to transport electrons. And there are several materials combinations around, and they distinguish from each other in terms of the materials in the electrolyte, and that also determines the nature of the transporting ion through the electrolyte. I will start with alkaline electrolyzers. Here, as the name says, the electrolyte is made of an alkaline potassium hydroxide immobilized on a support material. And in this case, the OH- ion, hydroxide ions, are the ones that travel through the electrolyte between the electrodes that are made of materials that are based on nickel. We operate this technology between 60 and 90 degrees centigrade. My next example is the proton exchange membrane electrolyzer. Here, as the name indicates, protons are the traveling species. The electrolyte material is a polymer, and the electrodes on either side are made of titanium, or on the other side on a carbon support material that is impregnated with platinum iridium. You can see these are noble metals. That is a slight challenge because apart from being noble metals and expensive, there are also limited resources on Earth. This electrolysis runs between 60 and 80 degrees centigrade typically, and that makes these two first examples low-temperature electrolysis technologies. My third example is a solid oxide electrolyzer, where the electrolyte is made of a solid oxide or ceramic material, and here the moving ion in the electrolyte is O2-, the oxygen ion. The electrodes are made on one side of a mixture between nickel and a ceramic material and an oxidic structure on the other side. In this concept, we want to have oxygen ions traveling through the electrolyte, and this requires higher temperatures. That is why this electrolysis operates between 650 and 850 degrees centigrade and makes it a high-temperature electrolysis. If I now have to select what do I want to install on my site as a customer, I would ask myself, how mature are these technologies? Can I purchase units? And what is the efficiency, which determines costs? And here I show the trend for maturity. Alkaline electrolysis is the most mature technology, while solid oxide electrolysis is the youngest in the row. On the other hand, the efficiency moves the other way around. Solid oxide electrolyzer offer the potential of the highest efficiency, and here I will show you some numbers. Regarding the size, we can see alkaline units in the 100 megawatt size, while solid oxide, the biggest units have now a size around 2 megawatt. And regarding efficiency, we can see that we can increase from a record alkaline 70% to 84% that were actually demonstrated on solid oxide electrolyzers in a system context. So these are the main materials of the cells, and in order to step over to a system, the first step is we are stacking these cells into a stack that is illustrated here in this cube. What do we have to add to arrive at the system? This is actually very much depending first on the type of electrolysis technology we are employing and also where we would like to employ it. But there are a few main components that are generic. Let us start with electricity part. So we of course have to supply the electricity for the process. And there can be several components in that part, like the supply, also converters, AC-DC, DC-AC converters. Next is we need to provide the reactant, water. Here we can also have a number of components. The aim is of course using seawater because we do not want to compete with drinking water. That means we have to do a certain degree of purification. We need to have removed the salts by desalination, ion exchangers. Maybe there need to be added some more filters for cleaning. And then we have to pump the water into the stack and to the cells and potentially evaporate it when we have a solid oxide electrolyzer. Then we obtain the product, hydrogen, the desired product, and sometimes together with water. So we need to have a separation and potentially drying of this gas. And all this is kind of surrounded by a heat management system that is either has to cool or to heat the system, and that is typically made of heat exchangers. So these are the major components in the system. And as mentioned, they vary a lot on the type of technology and the application. And to give you a bit more insight on this gas product separation part, I have here written in more detail what reactions we have at either electrodes in each of the technologies. And without going into all the details, you can immediately see in the alkaline electrolyzer, actually on both sides, we have a mixture of hydrogen with water and also oxygen with water. So if we want to have these as dry gases, we need to add some separation, could be condensation, and then we potentially have to dry the gases. And then there are also some small differences between PEM and solid oxide electrolysis, because in PEM you get a dry hydrogen, so because that is formed on the other side of the water, while in the case of the solid oxide electrolyzer, you have a dry oxygen, while hydrogen and steam appear together on one side. So again, here you would have to have a gas separation, maybe a recycling of gases back into the system, and a drying of the final product hydrogen. So this is how a system looks like in a very illustrative version. And how do they look in real life? What about the commercialization of electrolysis? There are immediate questions you would like to ask that are important to decide about installation of electrolyzers. There are some key parameters that I summarized here. That is, for example, how is the heat management? Am I working in a regime where I have to supply heat or to cool? Another very important parameter are, of course, costs. Here the capital costs, investment costs, how big do I have to make my system? And this can be translated back into a performance indicator, because the capital costs means how much hydrogen can I produce per time, and that is closely connected to the parameter current density. And the final parameter I've listed here is the cost of operating the system, so the running costs, and here this is closely connected to the efficiency that we have seen in the previous slides. And one figure here tries to condense all these parameters in one figure to give you a glimpse what is the status and also what is the potential. And let's start with the heat. When we are looking at this lower part here, that is actually a regime where we have to supply heat. When we are operating here in this regime, we have to cool the system. And then there are these two steeplet lines, and that are the thermoneutral voltages that I presented initially, where I neither have to supply or to remove heat. The other parameters are shown in x and y axis. In the x-axis, here towards to the right, we can increase the current density, we increase the hydrogen production rate, which is decreasing our capital costs. And on the y-axis, the efficiencies are plotted. So the higher the efficiencies, the lower the operational costs. And the colors indicate where the technologies are today and where the expected potentials are. And when we are looking, let's say, for the blue area, the PEM electrolyzer, they have a huge potential for increase of current density. So they are very much attractive in terms of lower capital costs. When we are looking at the other dimension, we see a huge potential for solid oxide electrolyzers due to their high efficiency. If we would like to point to a trend, then we would like actually to move to the upper right area, and maybe we don't want to exceed these steeplet lines. So this is depending on the whole integrated setup, if it's an advantage to be at this thermoneutral voltage or not. What this picture also illustrates, it seems that all technologies have their place and can make a benefit in the society. And that's also a message that we would need all kind of technologies to solve the challenges, production of hydrogen, power takes, etc. And the next, I will show you a few examples of where we are commercially. I start with alkaline, most mature technology, and here is a picture of one Chinese electrolyzer claiming the biggest one in the world, an alkaline electrolyzer, having a very impressive performance parameters and being able to produce large amounts of hydrogen, and it is available. The example for PEM is from ITM Power, another company, and they claim that they have the production facility with the highest capacity, so they can make the most electrolyzer units. And the last in the row is solid oxide, the youngest generation, and here is a picture of a German company, Sunfire, that shows a containerized module of a size of a few hundred kilowatts. And what they have already done and demonstrated is to combine a few of those modules into a 2 megawatt system that is installed in a harbor. So we see there are commercial or pre-commercial systems available for all types, where I just selected 3 examples. Now, in this list here, you see a bigger, let's say, status of what we have for the moment, listing the biggest companies in terms of production capacity. That is shown here with a study from a consultant agency. If you sum up the 15 biggest players, we see that we arrive at a total of about 22 gigawatt production capacity. So there is still a huge way to go, and we really need to scale up the technology in order to get to the targets of green hydrogen production and also to provide Power-to-X products. With that, I would like to finish the short introduction into electrolysis. I showed you that on the example of the water splitting, what are the basics, and in addition to water splitting, we can also do CO2 and co-electrolysis to arrive at synthesis gas to later on be able to synthesize green fuels that could be e-methanol, green hydrocarbon fuels. There are several types of electrolyzer technologies around that are distinguished from each other by different electrolyte materials, and then following also different electrode materials, different operational conditions and application sectors. When we are looking into the most, let's say, prominent examples, alkaline, PEM and solid oxide electrolyzers, then the majority is going down. The most mature technology is alkaline. The youngest is solid oxide. In terms of efficiency, the trend goes the other way. there solid oxide technology provides the potential of highest efficiency. There are commercial systems in the world, and there's a huge scaling effort needed and is also ongoing worldwide. So we hopefully can meet all the targets that we have set in different political frameworks around the world to arrive at a higher content of green fuels and green hydrogen in our energy and our society as such. With that, I would like to finish and thank you for your attention.